The waters in the ocean are in continuous motion due to multiple factors, some of which we've already discussed, some of which will be covered here in Chapter 15, and some of which will be more completely reviewed in a later chapter. We'll start with global circulation patterns before moving on to localized events. The circulation of the ocean's surface is controlled by wind patterns, which is controlled in the open ocean by the rotation of the Earth. If you look at the overall patterns in this image, you can see that there are generally loops of circulation known as gyres. If you draw a line along the equator, you can see the northern gyre's motion is a mirror image of the gyres in the southern hemisphere. We'll talk more about atmospheric circulation in Chapter 18, but basically winds from the equator to 30 degrees north and south latitude move west. Winds from 30 to 60 degrees north latitude and south latitude move east. Your book describes these patterns, known as the Coriolis effect, as the deflection of winds, and therefore the deflection of ocean surface currents to the right in the northern hemisphere and to the left in the southern hemisphere. Well, that's true for most of the ocean, but you might notice that there are a few places that don't quite follow that rule. Look at the Alaskan current and the Norwegian current. They don't follow the book's statement that northern hemisphere currents curve to the right. However, they do follow the pattern you would expect from the Coriolis effect. North of about 60 degrees north latitude, the patterns reverse and we would expect them to curve to the left. The same sort of happens in the southern hemisphere. The main difference is that the distribution of land is unique. The northern hemisphere has much more land, but there is water at the North Pole. Even though the southern hemisphere has less land, the presence of Antarctica precludes much ocean water south of 60 degrees south latitude. The effects of ocean surface circulation are perhaps most pronounced in Europe. The Gulf Stream, part of the North Atlantic Gyre, is bringing warm water and air from the equatorial region to northern Europe. Now, this is a fortunate artifact of the location of Europe and the coastline of North America. Much more northern cities like London and Berlin have climates more like Springfield than you would expect given how far north they are. Ironically, this could change and Europe could become colder due to global warming. Here's why. The white area on Greenland is all ice. Globally warmer temperatures would result in the melting of that ice. That fresh water would join the Labrador Current, shown here in blue, and because fresh water is less dense than salt water, it would stay at the surface, forcing the Gulf Stream to the south and preventing that warm water from reaching Europe. Now let's look at ocean circulation in 3 dimensions, starting again with the Gulf Stream. As the water moves north, it starts to get colder, which increases the density. Now, that water has also been on the surface for a long time, meaning that evaporation has resulted in increased salinity, also increasing the density. Now, this dense water sinks and eventually later upwells in the Indian and the Pacific Oceans, as the water essentially hits land and is forced up. Water in those areas brings nutrients up from the seafloor, so they're areas of high productivity. Now, there is an exception to this general circulation model. The deep water around Antarctica is so cold and so dense that it rarely upwells to the surface. Because most of the impacts of ocean circulation are seen along the shore, it's important to know the difference between the various terms to parts of the region. The shoreline marks the water's edge, and it changes continually. The foreshore is the region between the highest and lowest shoreline, and the backshore includes the land only affected by waves during storms. The coasts begin at the coastline and then extends inward. Except for rare events like tsunamis, ocean waves get their energy from wind blowing across the surface. The speed and physical features of ocean waves depends on the wind speed, the length of time over which the wind has blown, and the distance over which the wind has traveled over water. However, the movement of ocean waves is not just at the surface. Water particles move in a circular, vertical manner. that then cause smaller circular patterns below it. Now, this continues down until the motion is negligible, which is about half of the wavelength of the surface wave. In deep water, ocean waves are nearly symmetrical. However, as waves approach the shore, the seafloor begins to interfere with the vertical circulation of water particles. This slows the waves. New incoming waves start to catch up. Because the water can no longer spread out, it is then pushed up until it breaks along the shore. Waves rarely approach a shore straight on. Even when the shoreline is straight, the Coriolis effect causes waves to approach at a slight angle. When the shoreline is not straight, waves will be bent at different points as they hit the seafloor at different times. Wave refraction refers to this bending of waves. Waves will be bent toward any projections from land, causing headland erosion. At the same time, the wave energy in bays is spread out, allowing for deposition of sediment. Both processes make progress toward the same end result, a straight shoreline. Waves are constantly eroding and depositing sediment along shores. In the case of emergent coast, where the land surface has risen relative to the sea level, the first erosion feature to form is a sea cliff. Wave energy will obviously be greater at the bottom of the cliff, forming sea caves. If a sea cave eventually cuts entirely through a headland, a sea arch is formed. Although these are attractive, they never last. Gravity will win and the arch will collapse, leaving an isolated sea stack. These two are temporary as wave energy will be concentrated on the sea stacks. Once the sea cliffs are reduced to sand, deposition fills in any gaps. Most movement of sand is by the process of beach drift. Remember that waves approach the shore at an angle, carrying with it particles that are pushed up the shore at an angle. As the wave retreats, it moves straight down the shore. Therefore, there is a net movement of sand in a zigzag fashion along the beach. If beach drift moves sand to an area where there is no land, a spit will form. Eventually, the spit may reach land again, forming a baymouth bar, often just called a bar. Your textbook says that tombolos form in the same way as a spit, and that's not exactly correct. An offshore island will prevent erosion along the beach, but there is still deposition in that area. So spits form purely as a result of deposition, while the key for a tombolo to form is the lack of erosion. People have tried to harness beach drift to compensate for erosion. In some cases, people are just trying to increase the amount of sand on their beach for personal reasons. Unfortunately, that means the beach in the direction of the longshore current does not receive as much sand, but still experiences the erosion. To make up for that, the neighboring property owner may build their own groin. Jetties are effectively a pair of groins, and they are built to prevent beach drift from forming a spit and eventually a baymouth bar across the mouth of harbors. However, this is just a temporary fix. Eventually, the sand will build up and it will overtake the jetty. Breakwaters are built to protect boats and other property from wave activity. However, that disruption of waves means the sand is not eroded in that area. This means that sand must be dredged and redeposited downstream. And if that sand isn't removed, an artificial tombolo is created. One of the worst strategies to prevent damage from waves and storms is to build a seawall. The seawall prevents wave energy from spreading out across the shore, and instead that energy is focused on the beach. Not only does this speed up beach erosion, the seawall will eventually be destroyed also. St. Augustine, Florida, learned their lesson regarding seawalls, well, sort of. In part because of the seawall pointed out by the arrow. Erosion essentially removed all the sand from the beach. So sand was dredged from offshore and used to rebuild the beach in 2001 at a cost of about $16 million. And you can see the restored beach in the lower right. Unfortunately, replenishing the sand does not eliminate the processes that removed the sand in the first place. So in 2005, for another $16 million, beach nourishment was repeated. In 2012, it had to be done again, but this time for only about $14 million. Unfortunately, part of that recent attempt didn't even last a month, as a hurricane removed about 50 feet of beach. Realistically, the only way for humans to avoid damage from the ocean is to just stay away. The ocean will win any battle with your property. This is part of the reason why insurance rates in coastal areas, especially along the Atlantic Ocean and Gulf of Mexico, have doubled in the past decade, in the cases where insurance can be purchased at all. Tides occur continually in coastal areas, but at least they pose little potential threat to people and property. They result from the pull of gravity from the moon and the sun. When the sun, earth, and moon form right angles, the pull from the moon and the sun partially offset each other, as shown here, to form neap tides, where there is minimal difference between high tide and low tide. Even though the moon is much smaller than the sun, it has more of an effect on tides because it is much closer. When the sun, earth, and moon line up, spring tides occur. This is when you have the largest difference between high tide and low tide. Areas that are exposed to low tide only are called tidal flats. Most tidal flats are relatively small areas because there's not much change in sea level due to tides, normally. This place shown here is the Bay of Fundy in Nova Scotia, and it's a notable exception. Between low tide and high tide, there is almost a 50-foot change in sea level. This is some place that I can't wait to visit one day. In places like the Bay of Fundy, there is an immense volume of water that has to flow in and out of the area twice a day. The amount is so large that when the flood current comes in, rivers reverse their direction and flow uphill.